Okay, now we're going to get to the details about writing Lewis structures. We introduced them last week, but here are the directions. And like balancing equations, these directions are just more guidelines rather than follow these steps and it'll work out perfectly. So the first place to start is with the correct skeletal structure of the molecule. That means figuring out how are these atoms connected to each other. And sometimes you have several choices. So hydrogen atoms are always terminal. And terminal means on the end. Like at an airport terminal, those are those hallways that go off and they just end because that's where you get on the airplane, right? It's the terminal end. So hydrogens are always on the outside. They're never a central atom with lots of other atoms bonded to them. Why is that? How many electrons does hydrogen have? 1. When it shares 1 electron, it gets its duet and it's done. So it only forms 1 bond, ever. Okay, so it can't be in the middle, it has to be on the edge. Put more electronegative atoms in terminal positions. So if you're trying to decide, well, who's going to go on the outside and who goes on the inside, try putting the more electronegative ones on the outside. That's usually correct. Another guideline is that things tend to be symmetrical. These things are often symmetrical. And again, these are guidelines, they're not always true. Little boys usually like trucks, but not all little boys like trucks. Right? So after you do that, then calculate the total number of electrons for the Lewis structure by adding up the valence electrons for each atom in the molecule. So you go to the periodic table, you've got a carbon that's got 4 valence electrons, fluorine has 7 valence electrons, you just add them all up to know how many valence electrons do I have for the whole molecule. If you have an ion, then you have to think about the charge. Don't let the negative mess you up. If there's a negative charge, you add electrons. If there's a positive, you subtract electrons. Then you take those electrons and distribute them among the atoms, trying to give octets to as many atoms as possible. And of course, hydrogen just wants a duet, just 2. So hydrogen gets 1 bond, he's good, then you don't have to worry about him. So you start divvying up the electrons, trying to give everybody 8. And then sometimes you run out. You don't have enough. Well, when there's not enough to go around, that means we need to share more, right? So instead of just sharing 1 pair of electrons, maybe some people are going to have to share 2 pairs of electrons or even 3 pairs of electrons so there's enough to go around. This is one approach to drawing Lewis structures. There are other approaches. If you're good at one of the other methods, that's great. If not, I like this one. So let's do some practice. Write the Lewis structure for carbon monoxide. So the first step is figure out how are these connected. Well, there's only 2 of them, so that's not going to be a big deal. It must be carbon connected to the oxygen. Now, I think it's a good idea to just go ahead and put the single bond in there because there has to be a bond, right? And then we're going to look at how many valence electrons do we have here. How many does carbon have? 4, because it's in group 4. And how many does oxygen have? 6, because it's in group 6. So we have 10 valence electrons. And so I'm going to put those around and see what we can do. It might help you to put a dot at each end of this bond, because that's two electrons right there. 2, 4, 6, 8, 10. My approach is I usually just try to spread them around kind of evenly. So there's my 10 electrons. Did I fulfill the octet rule?
Yes.
Does everybody have 8 electrons? No. Yeah, I need a double bond. Because here, carbon, so how do we check? Well, you look at this element and you count how many electrons are around it. 2, 4, 6. And oxygen has 2, 4, 6. Nobody has enough. So that means we need to do more sharing. So I'm going to move a lone pair into a bonding position. So I'm going to take off that pair of electrons, and I'm going to put them in here. Whoops. I try to put them in here. I'm going to put them in there as a bond. I still have the same number of electrons, still 10 electrons. I'm just moving them around now. And so now I can look at this and see, well, oxygen has 2, 4, 6, 8. That's good. Oxygen's got the octet rule down. Carbon, 2, 4, 6, not quite. So we need to do more sharing still. So at this point, I have to choose, well, am I going to take a lone pair from oxygen or from carbon? I'm going to take it from oxygen. You're going to take electrons from the one that has more and make him share with the other one. Otherwise, I mean, you can do it, but it's just more erasing later. So I'm going to take that pair and make it a bonding pair. Still have 10 electrons. I'm just moving them around. Now this oxygen still has 10, it's 8, 2, 4, 6, 8. And now the carbon also has 8, 2, 4, 6, 8. Yay, we made them both happy. It's kind of ugly though. So let's write it nicely. So we have a triple bond. So triple line, oxygen, and then I have a lone pair on each of those. So there's a lone pair and a lone pair. And so here is my Lewis structure. Is that polar or nonpolar? Is carbon the same as oxygen? No, it's polar. Any questions? We're going to get a lot of practice with this today. Write the Lewis structure for H2CO. A lot of times, the way the formula is written sort of suggests the structure. So I've got 2 hydrogens, a carbon, and an oxygen, and I have to figure out how to put these together. The hydrogens have to be on the outside, and then I've got the carbon and the oxygen. I put the carbon in the middle and have the oxygen on the outside, or I could do it the other way around. Guideline is put the more electronegative element on the outside. So if I look at carbon and oxygen, oxygen's closer to fluorine, it's more electronegative. So I'm going to try putting the carbon in the middle and then putting the oxygen and the hydrogens attached to it. And later in the chapter, we're going to learn about something called formal charges that helps us to evaluate whether we did a good job of doing that. But for right now, we're just blindly guessing. Well, not quite blindly. So now yes? Well, that's an excellent question. Couldn't we just put them in a row like this? We could. Let's do both. And of course, this is the same as drawing it like this, right? It's just rotated around. Okay, so count up electrons. Well, I have 2 hydrogens. Each hydrogen has how many? 1 valence electron for each. And then I've got carbon has 4 electrons, and oxygen has 6 valence electrons. So this is going to add up to 12, right? Feel free to use your calculator to do that. I know we could all do that in our heads, but sometimes we make dumb mistakes and we get the wrong number of electrons and it screws everything else up. Just use your calculator. Okay, 12 electrons. So I have to count the bonds that I already stuck in there. And on this slide, I'm still going to put dots at the end of the bonds. So I've got 2, 4, 6 in there. 8, 10, 12. Let's see what happens over here. There's 2, 4, 6, 8, 10, 12. Are we done? No, because we don't have an octet, right? The oxygen here, 2, 4, 6. Carbon's good, 2, 4, 6, 8. Hydrogens always end up being good. And over here, the oxygen, 2, 4, 6, the carbon, 2, 4, 6, 8. So the oxygen doesn't have enough. So that means we need to make a double bond or a triple bond, possibly. Start with the double. So starting with this one on the left, I'm going to take electrons, non-bonding lone pairs, from the one that has more and share with the one that has fewer. So moving those 2 electrons over there. And now when I check things out, the carbon still has 2, 4, 6, 8. Now the oxygen has 2, 4, 6, 8. Good. Over here, we're going to need to move from the carbon also and share with the oxygen like that. And now we have 8 for both. So this is, like the primitive drawing, and now we're going to make it look nicer. So this would look like H, C, double bond, O, H, and a lone pair here. Oops, kind of got fat. And a lone pair here. Whether I draw the lone pair on the top or the bottom doesn't really matter. You do have to draw the dots. You don't need to draw dots at the ends of the bonds, but the lone pairs do need to be there. And then cleaning this one up over here. Oops. H, C, double bond O, H down here. And then this one ends up with 2 lone pairs on the oxygen. So we came up with 2 structures that satisfy the octet rule. Is one better than the other? Probably. Well, without knowing about formal charges, how could we tell? Well, let's think back to when we were drawing Lewis structures of elements. So carbon has how many valence electrons? 4, right? 1, 2, 3, 4. Oxygen has 6. 1, 2, 3, 4, 5, 6. And we can look at the number of unpaired electrons on those symbols, and that helps us to predict how many bonds it's going to make. So we can imagine this carbon, it's got these 4 electrons, it can share 1 each with something else to make 4 bonds. This oxygen, these lone pairs are probably all good by themselves, and it's going to share this one to make a bond and this one to make a bond. So you can imagine it making bonds like this, right? And this actually matches up with what the formal charges are going to tell us. So in this structure, how many bonds does the carbon have?
3 or
4. Because a double bond is 2 bonds, right? So the carbon here has 1, 2, 3, 4 bonds. And how many does the oxygen have? 2. Over here, the carbon has 1, 2, 3 bonds, and the oxygen has 1, 2, 3 bonds. So which one's better? This one's better. And we'll learn how to quantify that in a few minutes. Any questions? So with polyatomic ions, You add 1 electron for every negative charge. So if you have a 2 minus charge, you have to add 2 electrons. You subtract 1 electron for each positive charge. And then we write the Lewis structure in brackets and put the charge of the ion outside the brackets in its usual place, the upper right-hand corner. On Mastering Chemistry, I think they finally added the possibility for brackets. I looked at one, and you can do brackets now. Before you couldn't, and I was like, come on, guys. But they fixed that. Okay, so let's do a polyatomic ion. This is hypochlorite ion, ClO minus. So a diatomic molecule, we don't have to worry too much about how it's connected, right? They've got to be connected to each other. And then we add up number of valence electrons. Chlorine's in group 7, 7 valence electrons. Oxygen in group 6, 6 valence electrons. So you can see it's important to be able to identify number of valence electrons quickly, right? And thankfully it's just the group number, so it's pretty simple. And then that negative charge, what do I do with that? Do I add 1 or subtract 1? I add 1. Because this means it's got an extra electron, that's why it has a negative charge. So I'm going to add 1, and this is going to give me 14 electrons. So then I start throwing electrons around, and remember this bond is 2 electrons. You okay with me not putting dots on it? Okay. So we count that as 2, 4, 6, 8, 10, 12, 14. Cool. So chlorine has a pair of electrons, top, bottom, right, and left. That's 8. Oxygen, top, bottom, right, and left, 8. So they both have octets. We used up all the electrons. And the one thing we need to do is put brackets around this and put the charge outside. Because if we left the charge off, someone would be like, you're trying to write the formula for chlorine monoxide, and you don't have the right number of electrons. So the charge there is part of the structure. Any questions? Yes? Yes, we can do a harder one. We will. Any other questions? Yes?
So you don't have to do a double or triple bond with that?
No, you don't. So what you do is you spread the electrons out, and sometimes you have enough to give everybody an octet, and then it's all good. Because if we did a double bond now, we'd have too many electrons. We couldn't have octets. Because when you share, it goes farther. And so then we'd have oxygen and chlorine both with 10 electrons, and oxygen can't do that. So we will get to more complicated ones.